very much appreciate the chance to be here at Q2B again this year. Uh, Pretty incredible what a difference a year makes. But I'm also very excited to have a couple of our key partners involved in this conversation today. So I'd like to take the opportunity to welcome both Ilyas Khan, the CEO and founder of Cambridge Quantum Computing, and Christopher Savoie, the CEO and founder of Zapata Computing. We'll get a chance to hear from both of them a little bit later today, but I am tremendously excited to have them a part of this entire story. One of the things that I think we are most proud of this year is, as I talked about, we do have a very different environment, clearly. But in this environment, the entire ecosystem has come together to learn how to do quantum computing in the middle of a pandemic. How do you make relationships where you've never met somebody face to face? How do you continue to progress the era and the technology around quantum computing? And what we're seeing is having that play out over this year. Last year, I got up and in many ways introduced quantum computing and Honeywell to the world and said, why are we in this business? I talked about some of the businesses that Honeywell participates in. And I think I want to go back just for a second to share why that's so important. You know, Honeywell is in the aerospace business. We make control systems for some of the most sophisticated buildings, plants, campuses in the world. We make our own chemicals. We do process control for some of the biggest petrochemical plants in the world. We do automation of warehouses. We make personal protective equipment. All of that is brought together with a connected enterprise group that takes data from edge devices and does real-time artificial intelligence and machine learning today. Those are businesses that we are already in as Honeywell. And what's beautiful about that is that the technologies that underpinned our ability to go do that were critical for us being successful in quantum computing. It also allows us to have that domain expertise in each of these areas to really bring that to bear for not just our customers, which are the most important, but also ourselves. You know, Honeywell expects to be its own biggest and best customer in this. I talked last year about our trapped ion technology. In March, we communicated to the world and released a paper around our approach, which has to do with this quantum charge coupled device, QCCD architecture. And what's really critical about that is what you're seeing play out with Honeywell and our partners today, which is we make our own ion traps in our own foundry. And that gives us the ability to both develop the architecture from the bottom up, as well as make these traps extensible. What do I mean? I mean that we can release it like we have done today, and then quickly add in additional qubits to increase the capability. We have the precision to be able to do not just control of our qubits physically, but have developed zones so that we can have operations happening simultaneously across the trap, being able to do quantum operations in multiple places at the same time. It forced us to solve some really technical, difficult challenges along the way. And part of that allowed us to do synchronization so that we can maintain phase of these qubits as we move them around from one part of the ion trap to another. All of that played out in our ability to do very high fidelity quantum operations. What this amounts to for Honeywell is, in this early era of quantum computing, quality matters. The ability to get to the answer that you expect to get. What we have done over this year is just as we talked about in March, which was releasing a series of ever more capable quantum computers. What we have already available to our partners and customers are two systems, our system model H0 and our system model H1. In both cases, they presented a first in the world type of environment. So we were the first to have a measured quantum volume of 64. We were the first to have a measured quantum volume of 128. We have very long coherence times in our systems, very high fidelity operations. Being able to do that the way we have with our trapped ion technology means that we don't carry this logical swap error overhead. We do take longer. That is one of the things you're always going to hear about trapped ion. Certainly our version of trapped ion is that the transport of these qubits adds time, but it doesn't add error. And that makes it very critical for being able to get to the answer that you're expecting to get. We also have been able to take advantage of our controls expertise, our controls heritage in Honeywell, to do some very unique things in quantum computing. And that is this ability to do mid-circuit measurement, right? In the middle of a quantum computation, pause and interrogate specific qubits and say, what are you right now? Are you a 0 or are you a 1? We also have the ability to then, once you have measured that qubit, take and reinsert it. Now, it is no longer has the quantum information that it had before, but you're reinserting it as a new qubit in the computation. Between those two, we've then added that third piece, which is really critical, which is conditional logic. So what happens when during the computation, you say, I've measured this qubit and it's a 0, I want to be able to take real-time action. All of those have come together in the systems that we are now releasing and making available to our customers and our partners. What I said a year ago holds true today, which is this is not an academic exercise for Honeywell. This has never been an academic exercise for Honeywell. This is a business. And it's a business because these are businesses that we are already in. So our focus has been on real world use cases. I mentioned a few up here, but the work that we did hand in hand with Cambridge Quantum Computing and DHL, looking at cargo packing, the work that we did with Zapata Computing and Merck, looking at supply chain optimization that would go along with pharmaceuticals. We've also done work with Imperial College London and a very large electronics conglomerate, which I will probably be able to say when this goes live, but I can't say right now. As well as a global automotive company that we did in collaboration with Entropical Labs. And the important thing is each of these were building blocks on real use cases. This is an important time for quantum computing. This is the time where you build trust. You are able to take advantage of algorithms that are being not just contemplated, but put into practice on real quantum computers to see what can they do now, and as you increase this capability, what are they going to do in the future? And that trust building is critical. You just look at some of these organizations and say, what am I going to do with patient data? What am I going to do with some of the most important intellectual property that I have? Who am I going to trust to partner with to make sure that we are getting the answer that we need to have integrated into our operations? So it's a truly exciting time. I'll take the opportunity now to turn it over to a couple of folks. I'm very excited again to have Ilyas Khan, the CEO and founder of Cambridge Quantum Computing, as well as Christopher Savoie, the CEO and founder of Zapata Computing. Our interaction with both of these two organizations has been critical to our success. In full disclosure, yes, Honeywell Ventures is an investor in both of these two organizations. Done so on purpose because of the kind of brilliance and results that we have seen as we've gone along. We've had the opportunity to work with Ilyas and his team, tying in ticket and human into the quantum computers that we have today. We've had the opportunity with Christopher and his team to tie in Orquestra, the workflow software, into our quantum computers as well. And I'm excited to have them talk to you about what they've done. So, Ilyas.
Well, thank you very much indeed. A quick shout out also to Matt and his team at QC Ware for coming up with the whole vision of Q2B, which of course we were there at the first event and we're here today. A quick comment on CQC for those of you who might be not so familiar with who we are. We are a team of about 120, just over 120 people, primarily science-based. We've got over 80 scientists. and coming up to almost 50 PhDs now. The company is primarily owned by the people who work there. 70% of the company is owned by its employees, which I think is a key differentiating factor for us. We do have some external shareholders, which include JSR, a Japanese company in the material science industry, IBM, of course, and Honeywell. My senior colleagues on the scientific side include Bob Kuka and Ross Duncan. Marcello Benedetti is hidden in that group photograph somewhere, and my colleague Mattia Fiorentini, who runs quantum machine learning. I also want to mention Mehdi, who has just joined us and who runs business development. Is a year which marks a move to commercialization for CQC. Prior to that, we were, like many companies, in the R&D sector. And of course, ultimately, we are a business of first principles. What that means is that we have one problem that we solve, which is how do we make quantum computers usable by helping machine builders like Honeywell and users such as DHL. That's really the mission. Underneath all of that, what brings that to life is scientific innovation. I also want to comment on our work with Honeywell. We have many different touch points with them. They're a shareholder, as Tony mentioned. We have the privilege of being one of a tiny handful of people who are subscribers to the H1 system. We have run a commercial engagement with them recently that I'll talk about in terms of cryptography. We worked with them on DHL. We've been working on measurement-based error mitigation systems that have proven to be very successful. And many of you are aware that we're working on symmetry verification for making quantum chemistry that much more useful. On the cryptography side, we have implemented something called ARC, which is commercially deliverable today. So this is important because it's not just experimental. In doing so, we reached the highest level of Bell inequalities ever recorded. For those of you who are involved in cryptography, you won't need me to tell you what that means. Just a quick comment on the paper that I spoke about earlier. The import of all of that, and it's out there on arXiv, is that we can tackle problems where the systems are much bigger than the qubit count would normally allow. Much of this is based, of course, on the magic of Ticket. This is something which offers native programming interface and tools for runtime management. Ultimately, what it does, however, is create short, efficient circuits. During the course of 2020, we've picked up literally thousands of users worldwide, and we're increasing the user base. And this is open access. Anybody, for experimental purposes, can use Ticket and test just how efficient it is. Of course, it's a full stack that goes from the metal all the way up to the user. I'd like to finish my comments really by focusing on a grand vision. Of course, we're commercial now on cryptography. We're working on commercialization in other areas. But underneath it all, we're also largely in stealth up until earlier this year. Been working with Bob, whose Oxford team has been looking at meaning-aware natural language processing. Again, for anybody who's been involved in computational sciences, you will know the import of that. We ran the first quantum algorithm in this regard on the IBM computer, and we're looking forward to unveiling some pretty significant advances, including work with Honeywell's device in the course of 2020. And on that note, I'm going to hand back to Tony, and thank you again, Tony, for the work that you've allowed us to do all the way back from when we were a beta user of H0. Thank you.
Outstanding. Thank you so much, Ilyas. I appreciate that. That was wonderful. Christopher, would love to hear what you have to say.
Thank you for having me, Tony. I'm glad to be here to show some practical quantum computing results that we've gotten on the H1 machine. So I'm very excited to be able to show you something very visual actually today to show. Usually we're dealing in kind of abstract concepts of zeros and ones and superposition, all of that, and I don't have to do that today. I hope everyone's pretty excited to see something real and practical. So quantum circuit Born machine, QCBM, is at the heart of all quantum machine language models. We've seen it in the context of these bars and stripes types of experiments where you have some things that are bars and stripes, as you can see on the top there, or non-bars and stripes patterns. And basically, a quantum circuit Born machine can be used to find the distribution of those events. And as you can see, the proper probabilities that you would get in a normal case would be on the right there. Something that looks like that graph over there. And here is QCBM on Honeywell's actual system. You can see on the left what a score would be in the yellow on Honeywell, and in the green bars what the result that you would get on a noiseless simulator. So something a pretty much a perfect simulation of a machine with no noise. And as you can see at the end there, after the machine learning algorithm has been run, the result is that we do get the pattern that we just saw in the previous slide. Not only that, but the Honeywell H1 machine is performing as well as the noiseless simulator. So this is just a really great slide to give kudos to Honeywell for a really great system that basically performs as well as pretty much a noiseless simulation. And noise is really important, as we know, to get rid of in this context of quantum computing. So here you go. So using that, we use this QCBM in an actual practical application, quantum associative adversarial networks. You may have seen this in the context in the popular press as deep faking. And that's really what we've done here. So we've been able to use Honeywell's H1 classical computer. And this is the first time we're showing Zapata's classical quantum algorithm being used to use this QCBM algorithm to generate a high resolution handwritten digit group like those on the right here using the MNIST dataset. So QAAN, so these quantum adversarial associative networks, can be used to extend data sets for everything from image generation to credit card fraud or used in drug discovery and a bunch of other areas. But you're seeing on the right digits that were drawn by a quantum computer. And that's actually pretty cool. So, drawing fake people, you may have seen those kind of things. This is it. And this is pretty real. And if we go to the next slide, we can compare this to a Chinese university's results, which were state of the art as of late October this year. And those were the highest resolution photos we had seen in the literature on the left from a recent paper. And on the right, we see the image generated on the Honeywell System H1 built there and executed on a quantum classical workflow on Zapata's orchestra system. So I think picture's worth 1,000 words here. And we're really excited to show that a quantum computer can actually do some of these types of things that we're seeing on the right there. And it's really, these are really exciting times because this is getting very real. It's becoming really practical. And excited to be working with you on these kind of projects, Tony. Thank you.
Christopher, thank you. That was outstanding. It really is incredible to see the kinds of things that quantum computers can already do. One of the things that we've learned certainly is our interaction with partners and customers have informed our business models as well as our hardware. So what we've done with System Model H0 is to make it available as a usage-based model. But what we've found is that to make real progress, you need real time. And that often means tens of hours a month working on a system to be able to really make this progression, which is why we built a subscription model around the use of our System Model H1. The other thing that we've talked about recently is we have a plan to get from where we are today to 10 years from now. Many other companies have talked about that. I know we were getting questions about, does Honeywell really have a plan? Absolutely, we do. In fact, not only do we have a plan, we have taken many of the engineering steps necessary to execute against that plan. And that's important because as we make generation after generation of system, our approach is to make the system available, increase its capability very quickly, and make that all available to our customers and partners as they're leveraging their capability to drive new algorithms and real use cases with customers. And I think that's critical. in rapidly developing and progressing quantum computing for companies out there. I wanted to do a quick shout out. Tomorrow, Dr. Mike Vosvag, one of our theorists within Honeywell, will be talking about some of the unique things you can do with some of our capabilities around mid-circuit measurement and qubit reuse. And what we found is that it expands incredibly the kind of capability that you can get from a quantum computer. Finally, I'd just like to wrap up. So on behalf of myself, certainly on behalf of Ilyas and Cambridge Quantum Computing and Christopher and Zapata Computing, this has been an opportunity to work in just a unique era to be able to drive capabilities across the ecosystem. So thank you for taking the time today.